Again, I would like to welcome you all on behalf of IEEE Young Professional Montreal Group. This session entitled 5G Beamforming, Resetting Connectivity Performance is co-organized by IEEE Ottawa Young Professional Group, Polytechnique Montreal, and INRS Montreal. So today we have with us Dr. Muhammad Ali Babar Abbasi. He is a researcher with the Center for Wireless Innovation, CWI, at the Queen's University, Belfast. He is also a grand prize winner of the GSMA Mobile World Scholar Challenge in 2019 for his work on dual Rotman lines based 28 gigahertz beamformer. Towards the end of this session, we're going to have a Q&A. So please feel free to write in the chat box, and we'll take it from there and ask our presenter to have discussion on those points. So without taking any more time on my side, I would like to pass it on to Dr. Babar. And once again, thank you, Dr. Babar, for agreeing on, to speak on the beamforming techniques. So yeah, over to you, Babar.
Thank you very much, Intihab. Just a quick question. Can you see the screen now? Can you see
the
screen?
Okay. We can see the screen and we can hear you.
Okay, perfect. I will just test one more thing. I am trying to write something on screen, so can you also see that?
Yeah.
Okay, great. Thank you very much. Thank you very much. So welcome everyone on this section on 5G beamformers, resetting connectivity performance. So first of all, thank you note to Intihab, to Moin, to Shanawaz, and Ottawa section, IEEE Young Professional Montreal section, and Ottawa section, and INRS and Polytechnique Institute. Thank you very much for organizing the really good event, and I hope that we learned something today. So first, let's look at the content and structure of today's talk. We will go through what is in this webinar for you, and what is expected that you will learn from this webinar, and why you should spend your Friday afternoon listening to what we have to discuss here. So in first almost 10 minutes, we'll go through a little bit of definitions. I know it's more like a lecture thing, but I will just try to keep it as brief as possible. And then we will move to a big question. Why do we need beamformers? What is it that we cannot do with our general antenna structures, and why do we need beamformers? And then we will spend almost 30 minutes on beamformer classifications. Now, as a sub-part of those classifications, we will go through what are the latest trends and what are the future prospects, and what 6G beamformer should be look like, should be how connectivity can be possible using beamformers even in 6G. And then I like a structure in which we can have intermediate question and answer, because sometimes it is very sometimes the content is too much to absorb. So if Intihab allow me, can I just stop the presentation during this webinar and request for questions, if it is all right?
Yeah, it's okay. It's up to you.
Okay, perfect. Thank you very much. Thank you very much. So, okay, before so I will just minimize this excessive screen. Okay, so first of all, what is in this webinar for you? Together we are going to understand the role of antenna beamformers in 5G and beyond networks. Then we will review some latest trends and applications, and we will forecast future beamformer design for hyper-connected world. So about us, a little bit about us. At the Center for Wireless Innovation, we have a vision of underpinning technologies for mobile, medical, and space. So on the right side of the screen, you will see a building. Here is where we work. The Queen's University has Queen's University and the microwave engineering has a history of almost 60 years. So at this stage, we have almost 60 to 70 researchers and postdocs and academics working together to work on this vision that is underpinning technologies for mobile, medical, and space. So we have some incredible instrumentation and measurement facilities available here at the CWI, and one of which is this millimeter wave lab. That is kind of two of them are there in entire Europe. So we have one of them, and we try to work in the millimeter wave spectrum, and we want to see into the future what millimeter wave frequencies can give us and can provide us that we can utilize. So just one quick slide on overall research areas that CWI is working on. First of all, it is millimeter wave enabling technologies. So we want to see how millimeter wave can be used not only for mobile applications, but also for space applications, also for imaging applications, and even we want to go towards sub-wavelength frequencies and see how we can take benefit, because frequencies are natural resources and we want to get as much benefit as possible from them. There's just a matter of technology, and we want to use it. Then we work on mobile. We have done some enormous good work on in 5G. Some of our colleagues have actually developed first massive MIMO systems, and we also do a physical layer modeling for mobile that also involve 5G and beyond 5G. Just this year, we have started looking towards what 6G is going to give us. Then we also work on in medical field, the application of microwave and millimeter wave in medical, and then connected and autonomous vehicles. That is also a part of our hyper-connected world that we must be looking towards in almost 5 to 10 years from now. So before moving forward towards looking at what beamformers, a few definitions very quickly. So you may already have must have heard about the word antenna. So actually the antenna is an interface between radio waves propagating through space. I will just move this and electrical current moving in metallic conductor. So it's just an interface between electric field and magnetic field and currents and voltages. So the idea is, just imagine if we want to transmit our information from point A to point B, then if we use a wired connection, then we can have a metallic connectivity, and currents and voltages can be used to transmit our information or a signal from point A to point B. But what if we want to use free space to do that? Then we actually need an intermediate step between our voltages and currents and our electric and magnetic field. So using electric and magnetic field, we can transmit our energy or transmit our signals from point A to point B. So this portion, this interface between point A and point B is actually an antenna, and it's a definition about definition by the modern dictionary of electronics. So beamforming is actually generally achieved by using multiple antennas in form of an array. And antenna beamforming is the ability of an antenna array to steer maximum radiation towards prescribed direction, or conversely, the ability to estimate the direction of arrival of impinging signal. So it's just a book definition. Let's we will go into the details about what does it mean. So one of the most important equation that defines our beamformer application is this one, that is free space transmission formula, in which the received power at point B, that is, let us say this point, is actually equals to a combination of transmitted power, gain of transmitter antenna, gain of receiver antenna, and this whole expression, which involve C, that is speed of light, frequency F, and the distance between A and B, or transmitter and receiver, that is R. So in this equation, we generally know everything about what power means, what speed of light means, what frequency means. But generally, if we are not familiar with antenna applications, then we do not know about these terms, that is gain. So let's quickly go into the detail of what this gain is. Some dictionary definition. So antenna structure with non-zero length exhibits preferential energy radiation in given direction, theta and phi. And this property can be defined in terms of antenna directivity as the radiation intensity in given direction divided by the radiation intensity averaged over all direction. So what does it mean? Imagine if we have a point source or an ideal antenna, it should be radiating energy in all directions. What we want in real world is directivity or maximum radiation in the direction where we have something to provide our signal. Let us say our point B that we want to actually transmit our power into, and we want very less energy to be leaked in any other direction. And this kind of property can be wrapped into a definition of directivity and a definition of gain that is directly proportional to directivity with a factor of eta, that is efficiency. So let's not go into further detail. We will use this gain term and directivity term in upcoming classification. So we just need to know this definition. So mathematically, we can actually write the directivity down in terms of average radiation intensity and instantaneous radiation intensity in one particular direction. So one last definition, beamformer gain and directivity pattern along theta and phi can be represented in terms of a simple antenna element pattern multiplied by antenna array factor. So this array factor is a mathematical term that actually defines what kind of beamforming we can expect from a particular geometry of antennas. So if we know a single antenna element pattern, and if we know what kind of geometrical formation of an antenna array is giving us, then we can actually get to the beamformer radiation pattern. So for example, a simple antenna array with antenna elements placed like this in vertical will have a specific antenna array factor. And then same goes for this kind of antenna elements placed in horizontal and even randomly located antenna elements. So we can actually define this mathematical function that is array factor based on what we have to do. Let's look at one example. So imagine if I have two element dipoles, then the directivity pattern can be in terms of this, where maximum radiation is going towards X direction and almost no radiation is going along Z direction. So if I multiply this with this antenna array factor of again two antenna elements placed at a distance of lambda by 2, that is half wavelength, then actually I will get this resultant gain pattern. So whenever you will look at similar patterns in our upcoming discussion, then just realize it to be a resultant pattern of antenna pattern multiplication with array factor. So that's it for the definitions, guys. And let's move on to our important question: that why do we need beamforming? So the simplest reason of why do we need beamforming is can be demonstrated with this illustration. So imagine if I have a single RF source that is connected to multiple antennas, say 4 to 5 or 10 antennas, then all of these antennas will give maximum radiation along one particular direction, and due to destructive interference, it can have no radiation leakage in other direction. But here's the main problem. This kind of illustration will only make sure that we can transmit signal in one direction. So for example, if I have a B here, then everything is good. I can transmit my signal from point A to point B using a simple beamformer. But what if this B point moves here? I will have no control on radiating along this direction. So to do that, we need beamforming techniques. And one of beamforming technique is using sequential phase shifter array with each antenna element. So each antenna element, when connected to a phase shifter, for example, this one, then we can actually achieve beam scanning. It means that our beam can not only radiate in one direction, but the maximum radiation can be in other directions as well. So if I have this point B here, it moves along this azimuth direction, then I can actually scan my beam towards that direction. So this is one reason of using why do we need beamforming, and this is related to analog beamforming. We'll look at some other topologies as well. So in a communication system, beamforming focuses the signal energy in certain places and less energy is arrived in other places. So this concept is called space deviant multiple access. If you want to read more about this this definition, then please go through the lecture note that I have cited here. So what happens if we are using beamforming? We can serve spatially separated users simultaneously. So what does it mean? Imagine if I have a beamformer antenna here, and if I have a desired user, then I want maximum energy to be transmitted towards this desired user and no or minimum energy transmitted to this interfering user, that I do not want my signal to be transmitted. Or conversely, I want to receive maximum radiation from this desired user and I want no radiation from this interfering user. So a question arises, what should be the optimal beamforming should look like? So here is what an optimal beamformer should do. At the less SNR value or signal to noise ratio value, at the less signal to noise ratio value, we want each desired user to receive at least some amount of signal so that it can decode the information that it is receiving. So it can happen at the large distance from antenna. So imagine if this antenna is placed at origin 0 and this desired user is almost 1 kilometer away from the beamformer antenna, then my signal to noise ratio will definitely be less, giving other conditions. Then I want this desired user to receive at least some signal, and I want this interfering user to ideally receive nothing. But what if I move this mobile phone or this receiver very close to this beamformer antenna, say 0.1 kilometers? Then this is a high signal to noise ratio condition, and I want my power is no problem. My desired user will receive some power at least. But there is also an interfering user, and I don't want this interfering user to receive a very high signal strength. So ideal and optimal beamformer is kind of a balance between these two conflicting goals. So it will give us a very good, nice balance between providing power to the desired user and providing no power to the interfering user. So okay, that's more like a lecture part of this webinar, and we will then move forward to the beamformer classifications. And before going to beamformer classification, I will just stop here for now, and I will request, if you have any questions, then please feel free to ask.
I have a question.
Yeah, please.
Is this space division multiple access, is this already in 4G and 3G networks, or is this just for 5G?
No, it is. This concept is pretty old. So it is just like I can use space deviant multiplexing to differentiate between users in particular space. So for 5G, this technology is being used, but this technology has been there before.
Okay, thank you.
Yeah. So in case of direction of arrival, where does the intelligence lies? In the antenna end or the user end? I mean, how the feedback loop is formed. So Abdul Jabbar asked this an interesting question. The direction of arrival is like, I will try to give an example. Imagine I have 3 antennas, and what I'm doing, I am kind of reading the phase of signal that is received on this antenna. So if on the first antenna I'm receiving a phase of 0 degree, on second antenna I'm receiving a phase of 15 degree, and third antenna I'm receiving a phase of 30 degree of the same signal, it means I can calculate that there is a phase ramp. So this might be the direction of arrival. So intelligence is actually at the receiver antenna side, not at the transmitter side. I hope this I answered the question. Yes. Okay, great. Thank you very much. If there is any other question, please feel free to put it down in the chat window, and let's move forward to the next interesting part, that is beamformer classification. So just a disclaimer, this beamformer classification is more like what we will look in the future. It's not related to the beamformers that we have seen in the past. So we have done some research and some analysis and some brainstorming on what classification should we form looking into the future rather than into the past. So the first classification is based on architecture, and second classification is based on the frequency, and third one is based on the use case, but I will come to that. So in the classification based on architecture, we have analog beamformers, we have digital beamformers, we have hybrid of analog and digital, and we have lens-based beamformers. So analog beamformers and digital beamformers has been around for long, and there's already a lot of investigation happened here, so we do not need to go into the details of them. Just to give you a quick crux, an analog beamforming is actually each antenna fed by same, you can call it radiation source or a similar radiation source, and the beamforming is happening at the sorry, my pen is not okay. Sorry. Yeah. So beamformer happens when we are controlling the phase shifter. So we can actually transmit our energy in one direction or transfer our energy in another direction. While in digital beamformers, each antenna is connected to a signal processing unit separately, and beamformer happens virtually. You can call beamformer a conceptual beamformer happens when we have maximum power transmitted to one user and almost no power transmitted to interfering user. So this happens, everything happens here in the digital domain rather than the analog domain. Hybrid beamforming is a combination of both, and there's a kind of another variation of hybrid beamforming, that is lens-based hybrid beamforming. So the classification of based on frequency with respect to 5G and beyond, of course, there we can classify beamformers in sub 6 GHz based beamformer, for which some solutions are already available, and millimeter wave beamforming, which research is still focusing on the millimeter wave beamformers. And then use case in which we have fixed beamformer, it means any beamformer that is static in a channel, and then variable beamwidth beamformer. Some problems that we face with fixed beamformers can be solved by variable beamwidth beamformers, and then mobile beamformers, that any beamformer that we can carry around in a channel. It can be an autonomous vehicle, it can be our laptop, it can be anything. It can be a moving drone in the skies. So these kind of beamformers can be classified as mobile beamformers. So let's look at our first beamformer classification, that is based on architecture. Now, very quickly, the advantages and disadvantages of analog and digital beamforming and what we can see in the future. Analog beamformers are actually has very low power consumption. They do not need a lot of baseband processing because majority of things are happening in the RF domain, but they do not give us very good flexibility. So that's kind of a bad thing about analog beamformers. So we can connect multiple antennas with phase shifters, with lens-based systems, and we can scan our beam in entire azimuth or elevation direction, but that's it we can achieve using analog beamformer. However, digital beamformer are extremely flexible, and all the beamforming algorithms that we have seen related to even MIMO and massive MIMO applications that can be implemented in digital beamformer because they are flexible. But the problem is they have highest power consumption, and they require separate RF chain for each antenna to be connected to the baseband processing unit, which sometimes get a little bit complicated to build. Hybrid beamformer gets the best of both. So let's look at this illustration in which at one side we have digital signal processing unit, and at this end we have a beamformer. So we want this concept of providing the signal to desired users and avoiding our signal to be leaking in the direction where we don't want it to be. Imagine we have n number of antennas here, and then we have this L number of RF chains. So this entire architecture here can be any architecture. So this whole architecture other than antennas can be any architecture. But if our number of RF chains, that is this number L, is equal to the number of antennas, then it means we are dealing with a digital beamformer or a quasi-digital beamformer. But when the number of antennas is greater than this number of L, that is number of RF chains, then it means we are in the hybrid beamforming system. And if we just have one RF chain, it means that it's a simple analog beamformer. So in the majority of the system that we are seeing now for 5G implementation, we have hybrid beamforming, or in the future for millimeter wave, it is sometimes very difficult to implement MIMO and massive MIMO systems if we do not maintain this disbalance between the number of antennas and the number of RF chains, because RF chains are expensive, and we don't want to spend a lot on developing just a single beamformer. So there is another variation of this analog beamformer in which this problem of complicated structure between antenna elements and the RF chain is kind of solved by lens-based architecture. And we have seen a lot of examples in last 5 to 6 years. For example, the use of Lundberg lens can be a good variation of hybrid beamforming, and then spherical constant dielectric lens, and then flat lens, and then again a dielectric lens that is kind of that has a lens shape, and then Rotman lens-based beamforming architectures. So that's another variation of beamformers that kind of resolve some of the complexities that phase shifter-based beamformers give us. So if we want to look into the future, then we can differentiate a hybrid beamformer architecture into phase shifter-based beamforming architecture and lens-based beamforming architecture. So if we are using, if we want the RF front end complexity to be less, we would prefer lens-based. But if we want flexibility and scalability, we will prefer the phase shifter-based beamformers. And if we want, so it all depends upon what kind of system we want to build. So very quickly about the millimeter wave frequencies, analog, we cannot get away with analog beamforming, because the reason is, imagine if you want to implement a system, a massive MIMO system with 256 antenna elements, then it would be super expensive to connect all 256 antenna elements to a baseband processing unit and do all the calculations in the baseband in the baseband domain. So we cannot get away with analog beamforming, and there are multiple other reasons that we will go into detail. So for example, there is one architecture of there is one dia photograph that you can see in your screens, in which we have almost 8 RF chains here, but the number of antenna elements that we are using for this kind of topology are much greater than the number of RF chains here. So again, we are not going into the detail of the structure, but this work has shown that digital beamforming is possible at close to millimeter wave frequencies, and the results are amazing. If you are interested, please go through this work and get into the details. So another recently presented example of hybrid analog to digital beamforming architecture is this one, in which here we have a single input intermediate frequency, and we have multiple power dividers here. So these are Wilkinson power dividers, and then single RF chain is kind of converted into 8 different branches, and all these branches are then connected to a phase shifting network, and then going all the way towards the antenna array. And this is just one system. This is just one system with one input RF chain. And if we want to use this kind of architecture for serving multiple users, then we need to have more number of RF chains, and one phase shifting subarray is kind of shown in the right side of this slide. So another current example is this hybrid beamforming. Again, not going into a detail, but just to give you a crux of it, this work has shown that 64 to 256 QAM is possible at 26 gigahertz with the power of minus 36 dBm per channel. And this is kind of a proof that hybrid beamforming is good to be used at millimeter wave frequency spectrum at the very starting point of the millimeter wave frequency spectrum. So this work is also represent some blocker rejection for the interfering user, and that is what we are looking for. We want maximum power to be transmitted to the desired user and less power to go to interfering user. So about further classification of lens-based hybrid beamformer, we have seen two topologies. Again, majority of these topologies are from the past, but they are going to be used in the future. So lens before radiator is first topology, and the second one, lens is after the radiator. So what does it mean? Let's look at this illustration. Imagine if I have multiple antennas here, and we have an incoming wavefront here. Then if I bring each received signal into a lens structure, and this lens structure do whatever it is supposed to do and give us a power combined and phase shifted output from these output ports, then this kind of structure has lens before the radiator. So this lens body, that is the Rotman lens body, is actually before the radiator. And then there is some other topologies in which lens is actually after the radiator. Lundberg and constant dielectric lens and flat lens, all these are the examples of lens architecture in which we have lens after the radiators. So what happens here, the majority of the lens operation happens after the wave is emitted emitted from this radiating structure. So we can consider that this has a direct connection with a single RF chain or a switching matrix, RF switching matrix. I don't know, whatever topology is going to be used, it is possible using these kind of architectures. So one of the example that we presented here in Center for Wireless Innovation is this beamformer with Rotman lens based structure, in which lens was before our radiators or the antennas. So here we have 15 antenna elements in this rectangular structure, and these 15 antenna elements are capable of beamforming in 9 different directions. So this is just a representation that beamforming can be done in millimeter wave using these lens-based architectures, and this structure is scalable. The same architecture is scalable to even here we have demonstrated 15 antenna elements. We can go to 64, we can go to 1 to 8 elements, and the complexity and cost of these kind of beamformers is much less compared to simple phase shifter based beamformers. So another example of hybrid beamforming in which we have lens placed after the radiator is this one, in which we have a constant dielectric lens. It's just like a plastic ball with known dielectric properties and known electrical parameters. It's a little bit expensive to do a prototyping, but if we do mass production, then this kind of beamformers are pretty cost effective. So here we have multiple radiators connected to this beamformer, and if you look at this architecture in this kind of quasi-transparent illustration, then you will see that there are waveguide openings and horn feed openings, and each horn feed is kind of responsible for individual beamforming, and this whole architecture can actually build 51 beams in millimeter wave frequency band, that is 28 gigahertz. So this illustration is for 28 gigahertz. Again, it is scalable to 39 gigahertz as well. We have seen it in the simulation. So this is again another variation of a lens-based hybrid beamformer that can be used for millimeter wave frequencies and beyond 5G applications. So one very recent investigation that we have done here at CWI, and we have seen this before as well, is the direction of arrival estimation with only single RF chain. So generally what happens for direction of arrival estimation, we need multiple antennas, and we want to receive a signal in these multiple antennas and then calculate where that wave is coming, where the impinging wave is coming from. But using this technique and less lens-based beamformer, we have actually one lens architecture and this chaotic cavity, or you can call it oversized frequency diverse antenna, and then we have just single RF chain going out of this frequency diverse metallic cavity, and then just reading the signal in coming out from here, we can actually do the direction of arrival estimation using of course a technique that is given in this particular work that if you're interested in. So here we have shown that an incoming wave from a theta and phi can be estimated. We can estimate the direction of arrival of the impinging wave just using single RF chain, and that's kind of a huge hardware reduction, where on the same frequency band, if we are doing it using antenna arrays, then it will cost a lot. So this is kind of like very cost effective kind of a method. So I will stop here for now again, and I will request if you have any questions related to our first classification, that is beamformer classification based on architecture. Now we will quickly go through the frequency and use case, and I will stop here for now. Yeah.
I think we have a question from Nida. She's asking how beamforming in 2 dimensions is achieved.
Okay, beamforming in 2 dimensions. If we want to achieve beamforming in one direction, in one dimension, then we need either vertically placed antennas or horizontally placed antennas. And if you want to achieve 2-dimension beamformer, then we just need to have a rectangular based array architecture in which we can actually the vertically placed antennas can do beamforming along azimuth, and horizontally placed antennas can do beamforming along elevation. So I hope I answered the question.
So maybe I'm going to ask one question and it goes like this. So so in case you have simultaneous beams, right?
Mm-hmm.
And you have one receiver chain. So how are you going to make sure like there is no interference in between the simultaneous case, when you want to serve different users?
Okay, so this is actually a very good question. So a lot of processing is involved in this kind of simultaneous beam excitation and serving simultaneous users. It is pretty straightforward and pretty easy to actually serve single user, and it is also very easy to just connect phase shifting network with each antenna element to actually just tilt our beam towards the desired user. But it is difficult to actually do multi-beam excitation. So there are multiple algorithms that we have to use with the analog beamforming to make sure that only the desired signal is received, and everything else that we receive, we just discard it. So some baseband processing algorithms are used to actually decrease the power that is received from the interfering users, and just to get the signal that we're interested in. I hope I answered the question.
Yeah, thank you.
Yes, question.
Yeah.
Yes, yes, I have a question about if I come back to like a beamforming to talk about two dimension, azimuth and elevation. I want to know if like a MIMO antenna, MIMO antenna is that exactly 2 dimension, or you can have
Yeah, MIMO is an amazing technology. We will look into the details of what MIMO is in coming slides very quickly. But MIMO antenna, in MIMO antennas, if we have all antennas in a rectangular formation connected to a baseband processing unit, then we can achieve almost all the beamforming related problems. We can actually solve all the beamforming related problems. So we can serve multiple users using MIMO antennas. So if, for example, we have n number of antennas and we have L number of users, then we can do it just by connecting all the antennas to the baseband processing unit and just leave it into the channel. So this is possible using MIMO based. MIMO technology is kind of amazing, but it has its limitation in millimeter wave frequencies because some other problems arises when we move towards millimeter wave applications.
Okay.
I hope the questions.
Okay, thank you.
So there's another question: how to reach 2D beamforming by Rotman lens? So this is a very good question again. The Rotman lens is actually a planar structure. It can only help us achieve beamforming in azimuth or elevation direction. So imagine if I have a beamformer placed here, and if I have multiple plates of beamformer stacked together like this, and then I have another stage in which I have horizontally placed Rotman lenses like this. So two-stage beamforming can be achieved. So full dimension azimuth and elevation beamforming can be achieved. And there are multiple topologies that we have seen in the past as well, but now those topologies are kind of emerging again because that kind of structure is really amazing. So we can place vertical Rotman lenses, a number of vertical Rotman lenses for azimuth beamforming, and horizontal Rotman lenses as elevation beamforming, and connect both them together, and then connect the third thing to the antenna element. And if you look into one of our research paper on 28 gigahertz Rotman lens based beamformer, you can be you can actually look into the details. But it is very bulky. Is there an alternative? Yeah, this is a very good point. This kind of architecture is very bulky. So there are some new work that we are actually building on, that we are investigating. There is a technique called negative reflective index transmission line metamaterial, in which we virtually, using lumped elements, we virtually decrease the electrical length of a transmission line. So for example, if one transmission line is built on for one wavelength, imagine I have this pen and its length is one wavelength, then I can decrease the size of this length using a negative reflective index metamaterial based transmission lines. So we are trying to merge these two technologies in Rotman lens. It is difficult to do, but it is possible. So beamformers with Rotman lens based beamformers are actually bulky. There's another good thing: in millimeter wave frequencies, things are small, so you can actually put everything together in one small the mouse that you normally use with your computers. You can actually build a structure that is that small, so it won't be that big. But again, this is the problem that we are trying to solve. So how can we do, if we plan to do antenna radar with okay, field of view 120 cross 120, 120 cross 120 degrees is above 90 180. We can do that even using planar configuration. It's 120 cross 120 means from minus 180 till plus 180 plus minus 120. Okay, yeah. For this kind of configuration, we need to have at least 2 antenna configurations, or a shape that is not planar. I will give you an example. Imagine if I have multiple antennas placed on my hand like this. So I can actually increase the field of view, and using metamaterial or meta surfaces, I can actually make it a quasi-planar structure that gives me an illusion of having a bulge. So that is possible. Actually, this is possible, but I haven't done it so far. So field of view of 120 cross 120 is doable based on my understanding, but I haven't done it, so I cannot give you a right. I cannot give you a definite answer. Okay, so we have to be a little bit careful about the time as well. So let's move to our next classification, that is a beamformer classification based on frequency. So first of all, beamformer at sub 6 gigahertz, as I have mentioned before, MIMO and massive MIMO technology has kind of solved majority of the problems. So what this technology means: hundreds of antennas act phase coherently and serve tens of terminals in the same time frequency resource. So this technology was in past 10 years, a lot of work has been done in this technology, and based on our understanding, majority of sub 6 gigahertz problems can be solved using this one technology. So the main magic is the base station antenna array can actually acquire instantaneous channel state information and serve multiple users simultaneously. the future of sub 6 gigahertz, based on our understanding, is going towards cell-free massive MIMO, in which we do not have single antenna, single cell serving multiple users, but a lot of antennas spread all around. So one example is this, one very recent example is this Ericsson radio strip that operates at 3.5 gigahertz, in which we have this metallic strip which is connected to an antenna processing unit and these cross-polarized antennas. So if you look into this processing unit, then there are antennas connected to these amplifiers, and then a digital to analog converter, and A to D and D to A's, and then digital signal processing is happening here locally, and then it is connected to this strip. And this strip is kind of, it can be connected to, and it can be connected anywhere. It can be connected to buildings, can be connected to shopping malls or bridges, and they can actually serve many users without having the complexity that we normally see in current base station antennas for that we have been using for 3G and 4G. So this is one of the a very futuristic technology, and we hope that it will solve majority of the problems. So I will just say this for sub 6 gigahertz, because based on our understanding, majority of problems are solved, but millimeter wave beamforming is yet to be solved. So why do we need millimeter wave frequency spectrum for beamforming? First of all, large bandwidth, and there is one problem, that is high path loss, but based on beamforming technology, we can get rid of it. So this is as simple as this. Based on beamforming technology, we can get rid of the high path loss, because it has been shown before that if we have same antenna aperture, then if we use sub 6 gigahertz frequency, sub 6 gigahertz antennas are used for representing an antenna aperture, and if you use the same aperture for millimeter wave frequencies, then we can even enhance the path loss. So we can not only compensate the path loss, but we can enhance the power that is radiated from that antenna aperture. So it's kind of like this problem is kind of resolved now. And there's another thing, that the multi-path required to serve multiple users in millimeter wave cells are few. What does it mean? That if I have a millimeter wave based antenna, then I can, based on the scattering and the environment propagation, I can have multiple clusters, and each clusters can be served by separate beamforming antennas or beam directions. So for example, there is one cluster in one direction, and I can just throw maximum energy in that direction. It will end up in serving that one single cluster. So these problems are also kind of solved in past 2 to 3 years, but we are moving forward again. So this slide actually shows some of the problems and their solutions. It was assumed that in millimeter wave frequencies, we will have limited coverage, but this problem can be solved by simple co-siding. And we have multiple models that actually try to solve this kind of problem. And now we can actually have maximum coverage for all users, even if the environment, if the channel is pretty complex. So previously it was assumed that millimeter wave works only in the line of sight, but we have seen, due to the technology of beamforming and beam tracking and the reflection from the channels, we can not only achieve line of sight, but also non-line of sight. So previously it was assumed that beamforming is only viable for fixed users, but we have seen the millimeter wave frequencies to be used for high mobility scenarios, including autonomous cars. So this has been solved actually. So previously we assumed that we require large form factor for millimeter wave beamformers. If the number of antennas that we are trying to use is less, then form factor can be compromised. Then form factor can be small. So now commercial millimeter wave beamformers are actually available that can be mounted into very small devices. So this problem is also slightly, you can say, partially solved. We have not solved this problem completely, but partially solved. So that is one of the direction that researchers are moving. The beamformer at millimeter wave has two more consideration. One is spatial consistency and human body blockage. So if we have beamformers and our body can actually block a millimeter wave frequency signal. So this can be solved by placing multiple beamformers in multiple sides of or say this mobile phone. So for example, if I have one mobile phone with 3 beamformers all operating in millimeter wave frequency spectrum, then we can actually get rid of this human body blockage problem. Two very important resources for those of you who want to investigate further in millimeter wave frequency channel modeling and communication performance. One is this NYU SIM, and one is this Quadriga, and both of them are excellent resources to actually move forward with this millimeter wave, move forward with solving problems for millimeter wave frequencies. And these are two resources that you can use in combination with the beamformer hardware to see what performance you can get. So again, beamformer very recently, this Qualcomm Snapdragon and 5G modem RF has been released, which actually use 5G millimeter wave band frequency at 800 megahertz bandwidth, which is pretty huge. With 8 carriers and 2x2 MIMO, it has been shown that we can achieve almost 7.5 gigabits per second download speed and 3 gigabits per second upload speed. And this kind of RF transceiver can be mounted into mobile phones. So this problem is also kind of, this technology is at the very edge of where we are today. So people are pushing hard towards moving further with even more sophisticated kind of MIMO topologies and even hybrid configurations implemented in very small beamformers that we can move around. But still, we are not there yet. We are not there yet. So okay, again, I will just quickly stop here before going to use case, because we have to be careful about time as well. And if you have any question, please feel free to ask. Okay,
Dr. Baba, I have a question, please.
Yes, please. Yes, please.
If I'm asked to design a beamforming antenna, and on the other hand, if someone is asked to design a simple beamformer, for example, using the intelligent reflect surfaces, so is there any design difference between the two, or the main design consideration will be the same? And what are the technical differences between the two actually? One is the only IRS, and other we have full beamforming antenna.
Based on the recent work of Professor Emil Björson, his definition of IRS resides with non-active reflecting surfaces. So antenna has to be an active component. So that's the main difference there. But actually, the formation of beam and focusing energy in one direction is the same. So this concept is the same. You can call it. The concept is the same, but the practical implementation is different.
All right. Means in IRS we don't have a direct feed, but in antenna we do have a feed.
Yes.
Right? Yeah.
Yes.
Thank you. Okay.
Okay. I will move quickly towards the slide because we have very less time left, and I will quickly go through this third and final classification that is based on the use case. So fixed beamformers are the beamformers that stay consistent, that stay constant in a communication channel. For example, here, if we have multiple antennas, then this kind of whole structure, if it is fixed, then I can solve majority of the problems using the hybrid architecture and digital architecture that I have talked about before. But some of the problems with the fixed beamformers are, in some cases, we have more users at one side and less users in other sides. So for example, if I have a street, then and I want to serve that street and a park, then I will face more number of users in the street and less number of users in the park. So I need to have different kind of bandwidths serving different kind of users. So for that, this new technology of fixed millimeter wave beamformer with variable beam width is kind of very useful. Some of the information is available in this citation. You can go through that. So this is another example in which we have fixed beamformers, but we are leveraging the beamforming technology for our benefit and trying to connect or trying to reduce the trailing overheads in our communication structure using a simple radar array, again operating at millimeter wave frequency. So some of the information is this work is very recent, and it has demonstrated some very good application of millimeter wave beamforming. So again, another technique that we have seen in recent years is for fixed beamformers is compressive sensing, in which we can get to the same radiation performance of a beamformer using less number of antenna elements. So for example, in this case, we have 31 cross 31 antenna elements. We can get the same beamforming output or the same beamforming results using this 20 cross 20 elements. So compressive sensing is also one futuristic technology that we should be using, and we are using to some extent. And lastly, mobile beamformers, there are still a lot of problems to be solved in mobile beamformers. So far, millimeter wave 5G smartphones are in the market, but they are not, but the price is still too high. And we still are facing a lot of problems with using millimeter wave frequencies. That's why we in the mobile phones, we are kind of switching between sub-6 GHz and millimeter wave, depending upon the propagation losses at millimeter wave frequencies. So these are this is a quick illustration of in sub-6 GHz. We want almost entire mobile phone to radiate equally in all direction, but in millimeter wave frequencies, we want directional patterns. So that's it for today. In conclusion, we have looked at beamformer classifications. We have seen that the architecture can be based on if we classify it based on architecture, then we have hybrid beamforming and lens-based hybrid beamforming. Based on frequency, we still have a lot of problems with millimeter wave frequencies, but we are going to solve them in future. And there are a lot of problems here in the variable beam width beamformer and mobile beamformers that we are trying to solve. If you have any question, please feel free to send me an email. My name is Babar, and thank you very much. I hope you learned something today.
Thank you, Babar. Thank you for the comprehensive presentation. I learned a lot today, so I'm sure our audience, they have the same experience. So now if somebody has question, please feel free to write, or maybe you can switch on your mic. So we have one more question from Abdul Jabbar. Can you please suggest few good books to read or consult for beamforming antennas?
Oh, okay. This is actually a good question. Some recent books has been published by IEEE. I think one of the group in University of Glasgow has actually published antennas and propagation for 5G and beyond. So that is one very good resource. And I always consult with. I also get my consultation from some of the classic books, Balanese and Bozar. They are still very good resource to actually learn more about antennas and beamformers and antenna arrays. And one book from Professor Vincent Fusco about the theory of antennas and microwave, that is also a very good resource. Yeah.
So any more question?
I do have one quick question.
Yes, please.
Yeah, utilizing the millimeter wave in fast fading communications, like for example, V2X communications, vehicle to everything communication.
Mm-hmm.
Doppler plays a very crucial role here. I mean, in one hand, they say that the researchers say that beamforming is a promising technology for the V2X as well. But given the fast fading and the shortage of the signal strength in the receiver of interest, I mean, Is there any specific techniques for the V2X communication for those that require very high reliability? It's going to be like very fast switching between the beams.
So this is actually a very difficult problem to solve. If we look towards very fast switching millimeter wave beamformers that can provide very high radiating power or very high gain beamforming, then we may not be able to get to a reliability of 99.9% coverage or 99.9% of reliability of a network. So these are two kind of conflicting goals that we want to achieve using millimeter wave frequencies, but it's still a problem. I mean, we haven't solved this problem yet. There were a lot of myths about millimeter wave beamforming that has been kind of resolved now, but this one particular reliability issue is still there, and I'm not sure whether we will be able to solve it in near future or not. But a lot of research effort is going in this direction.
So this technology is like very suitable for nearly Cauchy static channels, like for those that they are Cauchy static channels, not near stationary. Okay.
Yeah, exactly. So millimeter wave is pretty good. Just imagine if I have a transmitter and receiver, they are going to stay there forever. Then I can use millimeter wave frequency with a huge bandwidth to transmit like gigabits to gigabits without any problem. But if I just move one either transmitter or receiver or just realign it, then things will not look good. That's the problem with millimeter waves.
I see. Thank you.
Yeah. Thank you very much.
I think we got one more question in Tikab, right? So someone asked, Goham asked about the Balanis as a reference. Is this a question or is it information? I didn't
You talk about Balanis. Balanis has done a lot of work in this field.
It's a question.
So can you please rephrase the question? I don't understand completely.
It's a question. It's my question because I.
Sorry, I cannot hear you. I think there's some problem with the bandwidth.
I don't understand you when you talk about.
Well, can you please write your question? We see a lot of people in your voice.
I want to know what is session. I want to know which kind of reference did you use.
So if I understand, he's asking the references from you. What kind of references that you can recommend him as a reference? Should he use the Balanis?
References do you use for this presentation? Okay, yeah, there are a lot of references actually, and in each slide I have used a separate reference, and all the references therein in the cited reference are also kind of my reference in an extension. So in every slide I have kind of given a quick citation. So if you receive the recording of this talk, then you will see that there are references in every slide, and you can go there, and then you can navigate through what I'm talking about.
So we'll be sharing the video. Actually, we're actually recording this session, so hopefully we're going to share it online on our website, or we'll share the video.
Okay.
Yes,
so
sure.
Yeah.
We will share it.
Okay, so anyone who is the official time of this talk is actually finished. So anyone who has another meeting or something, please feel free to leave the meeting. I will be here to answer if you have any question. I'm here.
I have one question.
So nice of you.
No worries at all. Thank you.
I have one question.
Yes, Amir.
Yeah, thank you very much for your very good presentation, and it was actually motivating to study more about this beamforming. But actually, my problem is that I've enjoyed the 5G in the millimeter wave from the wide bandwidths. And for example, in the beamforming, that's the construct with the lens. We have the different feed around this lens, and so if this blends with the one frequency, so we will have the some beam in the different directions. So as the, for example, in the 20% of bandwidth or 30%, that we are speaking about the wide bandwidth and ultra wide bandwidth in the 5G in the millimeter wave, what would be the direction of the beams as the frequency change? Is it predictable, or is it will change or not?
This is actually a very good question. I think it is better to just sorry, I will just pull in one more slide, and I will give try to give this information on the slide, if you will. So you have a very good question. So for example, if we built a beamformer, sorry. So for example, if we build a beamforming antenna for one particular frequency, just imagine I have a frequency changing here, and for the central frequency, I develop this beamformer, then it is going to give me one beam in one particular direction. And if I do all the beam switching and so on, then I can change its direction. So if I just slide this frequency to higher frequency or towards lower frequency, then of course this beamforming calculation will not be there. But if I limit my beamforming in such a way that my 3 dB beam width will stay in. So for example, this is my beam for this frequency. You can call it frequency A. This is my beamforming for frequency A. And this is beamforming for frequency B, that is here, frequency B here. Then there is a possibility that I can get away with serving a user that lies within this range. So this is kind of my limit of service. So we can narrow our beams with reference to one limit. Giving you an example, if you're trying to use 28 gigahertz millimeter wave bandwidth, then we should not go below almost 7 degree azimuth and elevation for one particular beam. So that is our minimum limit. If we go narrower than that, then there is a possibility that we will have shadow zones between our multiple beams. If we receive a signal that is at the edge of our frequency, say if we receive signal here somewhere, then we may not. I hope I answered the question.
Yes, thank you so much.
Yeah.
Dr. Waber, is the dependence of the beam direction on the frequency is related to the beam squint? Is it the same thing, or beam squint has some different interpretation? Can you please shed some light on this?
Beam squint, I have actually gone through it, but I don't know the actual definition of squinting, and it is related to the coverage area, you can call it, the
all right,
view or coverage area. I don't know actually the mathematical definition, so I cannot comment on is it the same concept or not. But yeah, sorry. But I should look into beam squinting more.
And also, given the abundant amount of the frequency available in millimeter wave, and using this technology to boost the efficiency even more. So using the techniques like frequency reuse, it's going to be useless, right? Like reusing frequencies, it's going to be useless.
Exactly. Yeah. So if we build technology, let us say if in next 5 years we build technology till say 60 gigahertz, then we don't need the frequency reuse at all. We just need to build our transceivers on that frequency, and just the power radiated by millimeter wave radiator will fade away anyway, so we do not need to do frequency reusing.
And this applies for the field duplex communications as well, because we don't need to use at least in-band field duplex communications to
yeah, exactly. Yeah, that's actually, these are the theoretical benefits that we were getting from millimeter wave. That's why we moved there. But when we started to build systems, then we know that there are a lot of actual problems, like actual hardware problems with millimeter wave frequencies. And yeah, but these you're absolutely right about that. Yeah. So yeah, are you working in the millimeter wave frequencies or?
No, I'm not working on millimeter wave, but it's like part of my my ongoing research.
Oh, okay, perfect. Yeah, it's an exciting field. I mean, it's the edge of technology. So
it's one of those promising technologies for like practical 5G, because we have 5G on paper and we have 5G on like TV shows, and so it's gonna be way to go to see practical 5G in coming years, especially.
Yeah. Millimeter wave 5G is still not as it sounded like in the marketing domain. So yeah, that's right.
And a lot of people are speaking about the environmental footprints that they reduce. So they are calling, hey guys, reduce the energy consumption, avoid to use high complexity solutions to address your problem of interest. So the millimeter wave in terms of consuming the power. So for the handset devices, of course, we have limitations. But I wonder if there is any ongoing research on the power consumption reduction in the base stations who are connected to the smart grid, that they don't have limitations, but still they consume a lot of power to do those complexities in the beamforming as well. Is there any arguments on the environmental footprints reductions?
Actually, for the power consumption, there has been a lot of work going on, and I may have mentioned it during my presentation. The recent Qualcomm a chipset, they claim to solve some of the power related issues, but specifically in terms of beamforming antennas in the base station, I am not familiar with a very extensive study which has kind of decreased the overall power that is required to make sure that they are working. Millimeter wave is power hungry. So if we use same radiated energy, and if EIRP is same, then we can go at least, you can say 10%. We can cover only 10% of the area that we previously were used to do before in 3.5 gigahertz using the same power. Power is an issue. So that's why we want maximum power to be transmitted only to the desired user and no leakage at all. No leakage. But I don't know how nicely we can do that in future.
Yes, I see.
Yeah.
So I think I won't bother you with one question. Is there any other questions?
Okay.
Do you have any questions? No?
So I think we can finish this session. And again,
okay, great.
Thank you to Dr. Babar and to our attendees. I think most of them, they are already left, but we still have 20 participants up till now. And thank you all very much for your attendance, for taking part in the discussions and all that. I wish you all the best, and I hope we have a wonderful weekend, and stay safe, and hope to see you soon. Thank you all.
Thank you very much.